think we should begin with getting this thing recording. Let's begin. Ryan, you had a question. You're saying many people have a question?
Yeah, with setting up 1.50.
Yes.
Yes.
And what is the problem?
Setting it up.
Have you tried?
Yes, I have.
Okay, may I see what you've done then? You can deal with that. You've used MathCAD before?
A little bit.
But you use it in other classes
I'm
too.
getting it down mentally, so I'm getting comfortable with
That's
it.
probably what's going on, is it's more about learning to use the software.
So let's see which side.
Do you have it? So that's something.
Yeah. Okay, so yeah, I got
No. So where is the code? Remember we talked last time? Okay, so you're gonna have to write a code.
Yes.
That's what you have to do.
Yes.
So write a code and we can talk. I mean, I'll talk to you about your code, but it's the same thing as what we talked about last time. Who else is working on this problem? Who hasn't started the problem yet? Who has finished the problem? So no one's finished the problem. So Phil, where do you lie on it? Have you started it yet? Okay. 1.50, so 150. The one where you solve it numerically for a initial angle, it's 20. All right, so this is a toughie because I don't know. Basically, all I can say is that we talked last time about how to do this problem, and Ryan, were you here last time?
No.
Oh, okay. So I'll have you watch my video from last time, I think, is what we'll do. Because I could write it right up for here. I don't know. How many of you guys have ever written a computer code before? How many have never written a computer code before? I'm just going to talk a little bit more than I should probably then about the answer, because I think that you learn by seeing it done a little bit. So with that in mind, I'm cool. Let's just go ahead and I'll tell you as much of the answer as I'm comfortable telling you. Hopefully it'll leave something to you. So the thing that we're trying to solve is the case where we have a skateboard and it initially starts at an angle of 20 degrees. And so here's the skateboard. All right, it's got wheels. All right. And we solved Newton's second for this previously in class, and I don't want to give it any more time, so I'm just going to write what Newton's second tells us in terms of this angle here, which we will call phi because it will vary with time. The phi double dot, the second derivative of phi with respect to time is minus g over r times the sine of phi. All right, and this is an equation where phi here is a function of time. This is an equation that is not analytically soluble, so we have to solve it numerically. All right, so you need to open up your MathCAD, all right? And you need to write, okay, I'm gonna leave some of this to you, how many steps you should do, because you want this thing to go back and forth, and you know the natural frequency is not going to change very much, so it's how many times you want to go back and forth, how many steps you're going to do. But let's go ahead and say maybe I will do, this won't be your number, but let's say I let I max, and I'll just make since I'm trying to show you what it would be in MathCAD, it's just a word, I'm sorry, it's just 4 letters in a row. And then to make something equal to something, what do we do in MathCAD? A colon. All right, so you type a colon, and you'll get this. You can even do colon and equal sign, it's fine. And then just put some stupid number in there. Whatever. Maybe it'll be good enough, maybe it won't. You could be smarter than that. And the way to be smarter than that is to figure out how many times you want to go back and forth, and I haven't memorized the problem, so forgive me. Let me go back and look at what we're trying to do. 2 or 3 periods, all right? Okay, so we want 2 or 3 periods to go by. So we can go ahead and start with this many. If you like this many steps, that's fine. If you don't think you get a good result with that, do more steps. You're going to get to figure out what T max is that we want it to be. So I'll show you where that comes in later. But this will be our number of steps. All right. Then we can go by, and you can either do subscript 0, subscript 1, it doesn't matter. In your thing before, I did sub zeros. So let's let T sub 0, or if you want to call it T1, if you want to count for, I don't care, will be 0. That's initial time. All right. And then I used F for phi, because we don't have Greek letters, I don't think, that we can use a math cat. Do we get Greek letters in math cat? Oh, well then do phi, don't do F. But I did F, so I'm just going to say that initially the angle was, say, 20 degrees, or you can do radians, it's fine, whatever. And instead of omega, because I didn't know you could do omega, I did W, because it's starting from an initial velocity, angular velocity of 0. And instead of alpha, I did A. And I knew that alpha was minus G over R times the sine of 20 degrees. You could have also written times the sine of F1 there if you wanted to, F sub 1. Okay. You guys know how to do this? Make a number with a subscript? All right. If you want to use the graphical user interface, there will be something that you push related to matrices, and it'll be the element 1. Okay? So these are the first element of a matrix. So far, so good. Sam, are you okay with this so far? Okay. All right. So we filled in the first element of 4 matrices. And so now what I'm going to do, oh, and by the way, before then, I probably should have let G equal 9.8 and R equal 5, or whatever it's supposed to be equal to. Yeah. Okay. Now I'm ready to do a loop. So I will, in that case, let I be equal to, which means make a colon, and then you'll get this colon equals symbol. And in this case, because I let 1 be my initial value, I'm going to sort of count from 2 dot dot to, what do I want to count to? Let's go with 5,000. To Imax, sorry. And then you can choose whatever you want that to be. That's fine. And then for each passing time, T sub I will be, well, some I over I max, or you can do it as I minus 1 over I max, whatever. So I'm actually changing the subscripts from mine. So I'm going to there might be errors in here. I'm just kind of hand wavy. But times whatever I want T max to be equal to. Do you guys agree with that? That should be some T max. So this is going to be your job to figure out what T max must be such that it is equal to 3 times the period of oscillation, right? Leaving that to you. Are you guys all right with that? Okay. Okay. So the next thing I need to do is to calculate my acceleration. And I'm just going to, just because I'm hand wavy, I'm just leaving this as I. You can decide how you want to do it. These are ticky-tack things you can make choices about. And you can do it probably far better than I can. All right. Acceleration at that time step is going to be minus G over R times the sine of F sub I minus 1 in degrees. Just note that that's degrees. And if you want to make that change to radians, it's fine with me. All right? So I want these time steps to be close enough together that there's a negligible change in phi during that amount of time so that this equality holds fairly well. Are you guys all right with that? Okay. So then I would say that my omega sub I, which I'm just going to use the W for, would be omega sub I minus 1 plus A sub I times, oh yeah, I should probably define dt. all right, and here I'm going to define dt as t max over I max. That's how much time goes by between steps. Do you guys follow that? All right. So in that case, I can say a sub I times dt. All right, fine. And then for phi sub I use f sub I. And I'm actually going to take Grant's advice on this one and do what his calc teacher told him to do. We'll say that it's f sub I minus 1 plus 1/2 omega sub I minus 1 plus omega sub I times dt. Hopefully you see that this is me plugging into this special case. Let me find my lecture notes from last time. That which I asked you to do last time in terms of solving the two-dimensional motion with quadratic drag, that could not also be analytically soluble. And so it's the same sort of thing where we get these initial values, and when we find the value 1 time step later and the value 2 time step later, then pretty soon we see, oh, that's it, that could be written as a computer code with a do loop. All right? So it's the same sort of expressions here, except that I took Grant's advice and I used v0x plus v1x and averaged them. All right. Okay, so wasn't it Grant that said that? Who was it that said that? Was that you? All right. Okay. Anyway, my code is done. I would like for you to plot f sub, and then you'll go to your plotting thing, which is clicking on a box and choose the xy plot, and plot f sub I versus t sub I, and you'll get the plot that you want. Is that clear? Are there questions about that? Could you write that? Does anybody here have a computing language that they're comfortable with already? Yeah, what do you like? Python is good. And if you prefer to do this in Python, that would be all right.
When you define I, is that like your while loop, essentially?
Yeah.
So you can just, you put your 2.
I is my counter. Like if this was, like, because you're saying, I don't know if, so, all right, say it one more time. I'm sorry. Let me understand.
When you make that statement, is that
Yeah.
like a while loop where you start it from,
Yes.
you run,
Yes, except normally with a while loop, you would at the end of it say, I equals I plus 1, go to line 100, and 100 would be here, and it would be a do while I is between 2 and I max. You know what I'm saying? It's less than I max. And initially you would have set it to I equals 2. Does that make sense?
Can you also set it up with Boolean and make it an inequality?
You could do that.
Okay.
With a less than sign, that would be fine as well. Yeah, and start it off with some value. You could write this in Fortran, you could write this in C, you could write it just, it would be a do loop or a go-to type of thing and a do while, or, yeah, that'd be what it would be. Yes?
So just to clarify, in MathCAD, would you just write 2 ...
MathCAD already knows that anything with that subscript I is inside of a loop where I is going to go through values from 2 increasing as integers all the way up to maximum value.
So once you define it at 2, then it just assumes that it starts at 2?
You can start it wherever you want to. So a lot of that, that's really what I want you, that's the type of question I want you to have and that I don't actually want to answer, because those are related to learning to do the coding. If you understand the physics, that's what I want to teach you, but I want you all to teach yourself this language. All right? So go online and read manuals and things like that. And yeah, go for it. Because in your future life, there will always be a language that you have to teach yourself, every now and then. Okay? All right. Is there anything else about that? All right, let's move on. The other thing that I need to say is that at the end of today, that's going to be the end of the material for test 1. So I need to set a time for test 1. And I think you're turning in homework here. You can return it here. So let's go ahead and do test 1 on Wednesday, September 28th. Does anybody have a conflict with that? So chapters 1 and 2, test 1. Huh?
I have an E&M test on
There's an E&M test on that day.
on the 27th.
Oh, well then you're good. Because I was going to move it to the 26th for you, but no, I think that you're good. Plus, yeah, that's going to happen. I think is that Fred's class? Whose class is that?
It's Fred's class.
Oh, well, great minds think alike, I guess. Yeah, I'm taking the 28th then. If there was somebody on the same day, that'd be an issue. I'm sorry. Okay. So test 1 over chapters. Let's go ahead and write that down. We'll cover all the content of chapters 1 and 2. And it will occur on Wednesday, September 28. Obviously, it is in class, right? Okay. All right. So, put that in here. Okay, then let's get on with our stuff for today. Motion of a charge in a uniform magnetic field. This is part 5 of the chapter. And the B vector with capital B will be used to represent magnetic fields. All right, so let's go ahead and imagine I've got sort of a 3-dimensional coordinate system here. And I have a particle moving. And I'm going to sort of choose my coordinate system so that the z direction is parallel to the direction of the magnetic field. That is the usual for a uniform magnetic field. That is usually the case, that you choose z to be the direction for the magnetic field. So I have, in this area, I have a uniform magnetic field directed like so. And so I'm going to go ahead and define that as the z direction. I also have a particle that is moving in an arbitrary way, like so. I don't know what that is, but and there's its velocity vector. You know, it might be that it has a little bit of a z component. It's not supposed to look like it's necessarily lying in the xy plane. All right, so when this is the case, we think back to 240, 250, or whatever calculus-based introductory course that you had. Our expression for the magnetic force is equal to the magnitude of this charge, Q, times its velocity crossed with the magnetic field. So that V cross B is the cross product of the two vectors, V and B. All right, and V is going to be very general. It can have components Vx, Vy, and Vz. All right. But B, again, we chose our coordinate system such that it has 0 for its x and y component and its full magnitude for its z component. Okay. So in this case, the first thing I have to do is calculate this cross product of V and B. And I remember it's the 3 by 3 determinant of the matrix, whose first row is x hat, y hat, z hat. The second row are the components of the velocity. And the third row are the components of the magnetic field. Okay, so now I'm ready to do my 3 by 3. So I've got this is equal to x hat times Vy times B. So I have to do the 2 by 2 determinant of what's left over, minus 0. Okay, minus y hat times Vx times B minus 0 plus z hat times 0 minus 0. Okay, and so my magnetic field, my magnetic force is equal to QV cross B. So here's V cross B. I just have to multiply it by Q to get my magnetic force. So I've got x hat QVYB minus Y hat QV sub X B plus Z hat times 0. Okay. So that is the force. And I'm going to have that this particle is moving in a magnetic field. And there's no electric field, so there's just the one force. All right. So let's go ahead and write Newton's second. Oh, and by the way, I guess I should draw on here free body diagram. So here's my charge Q. Free body diagram. All it's got is F sub B. I don't know. B cross B, maybe something like this. Yeah, all right. Okay, sigma fx equals max. Sigma fy equals may. And sigma fz equals maz. And those are Newton's second. All right. So in the z direction, I notice I'm going to get 0 is equal to maz, pardon me, and az equals 0. So I'll have a constant velocity motion in the z direction. All right, so we'll deal with that later on. And let's look now at sigma fx. So the x component of the force is q vy b. And that's equal to m. Now that I see that I've got velocity in my expression for force, I think I want to write my expression for acceleration in a way that relates to velocity as well. So I'll write that as v sub x dot. And for the y component, I've got negative q vxb for my y component of force. And I'll write that as v sub y dot, again, because I know my forces have that v term in them. And so that's going to be an important variable for me to deal in. Okay, so, when we did this problem in, whatever your introductory physics course was, we took this equation here and we rewrote it. I'll go ahead and do that. Vx dot is equal to QB over M Vy dot. I'm sorry, there's no dot on that. Scratch that dot. That looks bad. That still looks bad. All right, we'll just pretend that says Vy. Are you guys okay with that? And then what I'm going to do is I'm going to take a time, since these two functions are equal, the time derivative of the left-hand side will be equal to the time derivative of the right-hand side. And I get Vx double dot is equal to QB over M Vy dot. Except that I have an expression for Vy dot from this y component's equation for Newton's second law. So from that, I'm going to go ahead and make a substitution. I've got QB over M times whatever Vy dot is, which is negative QB over M times Vx. So I solved this equation for Vy dot, and I made a substitution where I saw Vy dot here. Are you guys all right with that? Jeremiah, are you all right with that? Okay. All right. So again, in 240, 250, we looked at that and we said, okay, well, that's not too hard. I've got Vx double dot is equal to negative some constant squared. I'll go ahead and call it omega squared times Vx. I only know two functions whose second derivatives are proportional to themselves with a minus sign. At that time, I only knew two. And they were cosine omega t and sine omega t. Both of them would work. Are you guys all right with that? Okay. So what I would say is the most general solution for this is that Vx as a function of time is equal to A cosine omega t plus B sine omega t. Sine omega t. All right. And then remembering that Vy dot, that Vy, is equal to 1 over omega Vx dot, then I'd go ahead and take a derivative. I get Vx dot. So that'll be A times negative sine omega t times omega, but I've got a 1 over omega out front. Plus 1 over omega times the derivative of this guy with respect to time. So 1 over omega times b cosine omega t times omega just gives me b cosine omega t. And if I want to know what a and b are for each of these, again, this isn't exactly the solution I want to present to you, so I'm going to go just sort of hand wavy with it. Clearly, a must be equal to, if I just evaluate the boundary condition for this equation, the Vx equation for when t is equal to 0, I find that a must be equal to v naught x. And if I evaluate this equation for when t is equal to 0, I see that b must be equal to v naught y. And let me make sure I didn't make any math errors because I'm good at those. All right. All right. So, and this a here is still v naught x, and that b there is still v naught y because they're the same solution. All right. And then I can also go on from there, because really what I wanted was not v as a function of time, although I have it now. I wanted location as a function of time. So in that case, I would note that x as a function of time is equal to the integral of Vx t dt. Not sure I like that very well, but okay. All right, and so anyway, all right, so I will get something again. I'm just doing things that are rather hand wavy here. I'm going to get for my expression, I've got to integrate this guy as a function of time. So I've got v naught, and you know what, I'm not even going to worry about that. Let's just use a cosine omega t plus b sine omega t, because I'll have to reevaluate boundary conditions to get what the resulting constants mean. So Vx as a function of time is a cosine omega t plus b sine omega t. And I'm going to have to multiply, in order to do this integral, my dt by omega, which is going to give me a 1 over omega out front. So I'm going to get a over omega times the integral of cosine omega t times omega dt, which is sine omega t. And I'm just going to do the indefinite integral right now. We'll talk more about the exact solution when I solve it a different way. All right, plus b over omega, because I need to multiply this guy by omega to get the proper Jacobian to multiply my dt. So I've got plus b over omega times the integral of sine omega t times omega dt, which gives me negative cosine omega t. All right, and y as a function of time is equal to negative a over omega and negative cosine omega t plus b over omega, read this guy, times sine omega t. All right, so now evaluating at, should I do plus the constant? Sure, we'll just leave it in this form. There could be a constant here which would tell you the center of the circle, but all right. So x at 0, yeah, sure, I guess I should do, yeah, all right. X at 0 is going to give me, this guy will be 0, so I'm going to have this negative b over omega is x naught. So I'll just go ahead and do it this way. B over omega must be equal to negative x naught. How's that? And when I evaluate t, or y at t equals 0, and I see this guy is 0, and y naught must be a over omega. Okay. Same thing here, that must be y naught, and that must be x naught. So this is sort of how we solved it when we did 240, 250, or did your calculus-based intro. And so your final solutions, I guess it doesn't kill me to write them. X as a function of time is equal to x naught cosine omega t plus y naught sine omega t. And in 240, 250, we always had this object going about the origin. And a circular path in the xy plane. Y as a function of time then was equal to y naught cosine omega t minus x naught times sine omega t. And that was the solution we got before. And we noticed that the object, as a result, oh, and by the way, z as a function of time is equal to z naught plus v naught z times t. That's your location. That's your location of your particle as a function of time. And we see that what happens is that this particle, as it's traveling through this magnetic field, goes in a helix. All right? In terms of its z component, it's moving at a constant velocity. In terms of its x and y component, it's following a circular path, sort of helically in the direction of the magnetic field. And again, in 240, 250, the center of that path was always chosen to be the origin of your coordinate system, which is why this expression works. All right. So let's move on to what we want to do. Because we've already seen that way. Now what we're going to do is we're going to do the same problem another way. It's actually a more general way, which is nice. But the other nice thing about this other way we're going to do it is that it's going to use complex numbers. And I want to do this also for the purpose of introducing just the math related to complex numbers. Okay. So let's get rolling. So I still have the same situation that I had before. And I have, so everything up to here, everything up to right here is still going to hold. I'm not going to redo it, okay? It's all the same. It's just here I chose to get my solution by taking a second derivative and then finding an answer. Now I'm going to do things a little bit differently. So I am going to let this letter eta, which looks like an N with a long tail, equal my particle's x component of velocity plus I times my particle's y component of velocity, where I've introduced I, which is the square root of -1. All right. If that is the case, then n dot, the time rate of change, I'm sorry, eta dot, the time rate of change of eta, is equal to vx dot plus I vy dot. All right. Going back to my previous expression, here, all right, I have, well, what do I have? I have Vx, we'll go ahead and say where, from Newton's second law in the x direction, Vx dot is equal to QB over M, which I also chose to call omega later on, times Vy, where omega equals QB over M. I need to give myself more room for that. Okay. I also have, from Newton's second law in the y direction, Vy dot is equal to minus omega Vx. Oopsie, Vx. All right, so I can plug that in here, and I get that eta dot is equal to Vx dot, which is omega Vy, plus I times Vy dot, which is negative omega Vx. But I have a sign error here, maybe. Let me make sure that I don't have a sign error here. No, I'm okay. All right. So where was I? Vy dot negative omega Vx. Okay. Now, if I look at that for a while, I say if I factor out a negative I omega out front, because that's the thing that's multiplying Vx, I want to see what I get. I get Vx plus something. Figure out what the next term should be. Yeah, that's fine, but we don't want your I, let's not have the I in the denominator. All right. So this is fine for this first term. I'll go ahead and do it because it does look like these complex numbers are a little bit confusing. So I've got a plus for this term here, omega times Vy, which is positive 1 times Vy, which is also known as I times negative I times omega Vy. All right, so if I want to factor out the negative I, omega, I'll get Vx plus IVy. And then what I see at that point is, oh, this is equal to minus I omega times eta. All right, which tells me that my eta function is, a function of time, obviously, is just a constant times e to the minus I omega t. Again, that's the only function whose derivative is proportional to itself, and the constant proportionality is the thing that must multiply t in the e to the blank times t. All right. So now the thing that we need to think about, because we realize I've got a complex function here, but if I found this function, it'd be great, because I know its x component is equal to Vx, and its y component, its real part is equal to Vx, and its imaginary part is equal to Vy, and then I could go from there and solve for location and x and y components of location as a function of time. All right, but before I do that, I need to do a little bit more with just these complex exponentials, because this is what we have here. And also, by the way, a can also be a complex number in this most general solution. All right. All right, so if I Taylor expand e to the z, this is just simple Taylor expansion, 1 plus z squared over 2 factorial, I believe it is, plus z cubed over 2 factorial, over 3 factorial, plus and so on. Remembering that 3 factorial is 3 times 2 times 1. Okay. So in this case, let's say that I had, should I just do a second line or not? Let's say that I want to think about e to the k times z. I've got 1 plus kz plus kz quantity squared over 2 factorial plus kz quantity cubed over 3 factorial plus and so on. All right. So if I want to take the time derivative, I'm sorry, the z derivative, sorry, of e to the kz, I can just use a really simple sort of chain rule here. I'll have 0 plus k plus k times, let's see, 2z over 2 factorial, so that would just be k times z, plus k squared, so I'll just have it k times k times 3z squared over 3 factorial. The 3's will cancel. I get z squared over 2 factorial. Plus so on. And I needed a k squared there for that to be right. Okay. So hopefully you see now that this is just equal to k times e to the z. I'm sorry, e to the kz. Wait. Hold down. I dropped a k here too. That should be a k squared, so I need a k times that. All right. So k times e to the kz. All right. So that's a nice result. We sort of were hoping that that would be the case. Now, the nice thing also about expressing this as a series expansion is that I can think about it in the case where z could be maybe a purely complex number, a purely imaginary number, in which case we would write that as e to the I times theta. Without loss of generality, that is fine. And I would get that is equal to 1 plus I times theta plus, how far out am I going to take this? I times theta quantity squared over 2 factorial plus I times theta cubed over 3 factorial plus I times theta to the 4th over 4 factorial. That's as far as I'm taking, because that's all that will fit. Okay. And what I have is I can gather up all my real terms, and I'll get 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial. Plus, minus and so on, plus I times theta, that guy will have it, minus theta cubed over 3 factorial, plus and so on. All right, and if I carried out that each of these series even to infinity, I would see that this is equal to the cosine of theta plus I times the sine of theta. Right? And this equation has a name. It is the Euler equation. And we'll be using it a lot. Okay. We should note also that this result, what we're looking at here is, if theta were to vary in time like an omega t, we'd be looking at a circle of possible values where this is sort of the real axis, real, and this is the imaginary. And this, as a result, the length of this sort of radius of this circle is obviously the real portion squared plus the imaginary portion squared, which is always going to be equal to 1. All right, so that's like a unit circle in the real imaginary plane. All right. So what else do we need to know about complex variables? I think I mentioned it, but I'll be more clear right now to note that in our solution, for eta, I had eta is equal to a e to the minus I omega t. And that's interesting because eta's real part is the x component of velocity and eta's imaginary part is the v component of velocity. But in this expression, I have to remember that this a is a complex number. That doesn't mean it's imaginary. It means it has a real and an imaginary part potentially. All right, because this is the most general solution. All right, so let's go ahead then and note what that means is that I can write eta as, clearly, not skip a line. I can rewrite a as having, some magnitude a, and then e to the I times some constant, which I'll call delta, lowercase delta, e to the minus I omega t. So what that's doing is that's taking a complex number, like say one that's here, maybe it's a complex number that has that real and imaginary part, and if I don't, vary theta, then if I just multiply by a constant, that constant out front will be equal to the magnitude of that complex number. All right? And I can just include this e to the I del term to tell me sort of the phase angle in the real imaginary plane. You could have also written this thing here as some sort of x plus iy type of thing that we're used to, although we use x and y for location. So let's think about c plus I times d. I could have done that. And there I'd be writing a complex number in terms of its real and imaginary parts. That's fine. But without lost generality, I can also write it this way because it still is dependent on 2 degrees of freedom. That's a, which is now the magnitude, not the magnitude of the real part, just the overall magnitude of the complex number, and del, which is the phase angle for that complex number in the real imaginary plane. Okay? Are you guys all right with that? Cash, are you okay with that? All right, cool. All right. All right, so I could also note that I can simplify eta and write it as a e to the minus I omega t minus del if I want to, in that case. All right. So let's continue on. Oh, I've got 1 minute. With our solution. This is the solution for a charge in a magnetic field. Okay. First of all, I already knew AZ was 0, so Z as a function of time is Z naught plus V naught Z times T. Okay. Now, what I am going to do is I'm going to introduce a brand new variable, C. And Xi is kind of like a zeta except with an extra squiggle. So zeta looked like that, and Xi looks like that. All right? And Xi is going to be equal to our x component of location plus our I component of location as a function of time for our particle. And so what that means is that this thing that was called eta is going to be equal to Xi dot. All right, so what that means is I can find Xi because it is equal to the integral of eta with respect to time. The integral of a e to the minus I omega t dt. To get my Jacobian right, I have to multiply by minus I omega. So I'm going to have an I over omega out front. And I've got I over omega times a. Again, this whole chunky thing is just a complex number. Times e to the minus I omega t plus b for my indefinite integral there. And we'll take this whole thing out front here, and we're going to call that capital C, because it's just some stupid complex number. Then we're going to use boundary conditions to figure out what b and c must be, and we'll have our solution for x and y as a function of time in the first couple minutes next time. Your homework is still due Wednesday, except if you would like an extension on problem 1.5 until the following Monday, I'll give it to you. So you can turn in all of it except for the first one if you'd like to tomorrow, Wednesday. And you don't actually need this final solution to do your homework, so there's no reason to hold that up. All right, I will see you Wednesday.